Welcome everyone to my devlog of the Tiniest adventure, an action RPG project I built in Unity 6 URP. This is a gameplay focused demo. It takes a step back from story and works more like a compact gameplay playground where the player can explore an island, fight enemies, talk to NPCs, acquire new weapons and customizations, unlock abilities, and save their progress. For this devlog, I'm going to break down the main systems behind the project with an emphasis on combat, weapons, dialogue, UI, locomotion, and enemy AI. The goal of this project was to show that I could build scalable gameplay systems, create designer-friendly tools, and connect gameplay, UI, camera, animation, enemy AI, and save load into one cohesive playable prototype. There are smaller systems that I won't go too deep into, but they are included in the demo to support the overall playable loop. Before we start, I want to add a bit of context behind the project. This was built in around 9 months, although the first few months were lighter because I had another project and other things going on. I used asset packs mainly for art and audio so I could focus on gameplay systems, implementation, and integration. I also used Unity tools like Cinemachine, NavMesh, DoTween, and the input system. The main focus was to build gameplay systems you would see in action RPGs. The player might notice certain mechanics inspired by games like Breath of the Wild and Final Fantasy VII Remake, but the goal was not to copy those games. The goal was to build a small polished systems demo around combat, progression, dialogue, and exploration. With that in mind, let's get into the project. Let's start with the architecture of the code. One of the main foundations of the project is the Finite State Machine System. I use it for player locomotion, enemy behavior, enemy combat, and other state-driven systems. The base Finite State Machine registers state classes in a dictionary, keeps track of the current state and next state, and handles transitions. Each state has an enter, update, and exit function. When I call goTo state, the Finite State Machine does not instantly switch states. It queues the next state, and on the next update, it exits the current state, enters the new one, and resumes update calls. The reason I like this approach is that it avoids changing states halfway through logic. It also keeps transitions more predictable because state changes are queued instead of immediately interrupting whatever is currently running. By design, because only one transition can happen, transitions don't overlap. Before this, I would usually handle states with enums and big switch statements. That works fine for smaller mechanics, but for a project like this, it can get messy fast. Everything ends up in the same class, the update function gets crowded, and adding new behavior becomes harder to manage. With this FSM setup, each state has its own class and its own context. So adding something like dodge, knockback, swimming, aiming, or enemy strafing becomes more organized because each behavior lives in its own state instead of being mixed into one giant update loop. Something I'd improve in a future version is the way states are referenced. Right now, I use strings because they are readable, but strings are type prone. I'd probably move toward constants or enums. I'd also consider a small request enter or request exit layer so certain transitions can be validated before they happen. For the kind of action-heavy project I was building, this pattern became one of the most valuable parts of the codebase. A few other patterns show up through the project too, though. I use scriptable objects for data-driven systems. I use interfaces so systems could talk to each other without depending too much on concrete classes. I use the UI input module for the button navigation in the pause menu, and I use token animation callbacks so things like enemy attack cooldowns only begin after the correct animation finishes. For player locomotion, the challenge was not moving the player. It was making one movement system support many different movement actions. The base movement function is similar to what I've used in previous projects. It takes player input and camera orientation to determine the movement direction, makes the movement slope aware, creates a target velocity based on movement direction and max speed, and then drives the current velocity towards that target. The important thing I noticed was that the movement formula itself did not need to change much between states. What changed were the variables, and not just the speed or acceleration, but also inputs and movement via overrides plus service switching, so I made those parts overridable. That let me reuse the same move player function pipeline across different locomotion states instead of writing completely separate movement logic for every state. The downside is that the locomotion base became one of the more crowded classes in the project. If I rebuilt it, I'd probably extract more helper structures, especially for shared logic like hit stop. One decision I want to mention is rigid body versus character controller. For the player, I used rigid body because I wanted more flexible and a more physics-friendly feel. Certain safeguards of character controller like skin width made some movement mechanics harder to tune. For example, with a dash attack, character controller skin width could keep the player slightly too far from the enemy, which made the dash attack feel like it stopped short. I could have disabled the controller during the dash and handled movement another way, but at that point, it made more sense to use rigid body for the player. For enemies, I use character controller because enemy movement did not need the same flexibility. It benefited from being more controlled and forgiving with things like skin width and step offset. In hindsight, I might experiment with rigid body enemies in a future project, but for this project, character controller worked well for the enemy behavior I needed. For combat, I wanted something with the flexibility and simplicity of Breath of the Wild, but with a bit of the faster energy of Final Fantasy VII Remake. The combat system supports 4 melee weapon styles: single sword, two-handed sword, spear, and dual swords, plus bow and arrow. It also has a dash attack inspired by Cloud's dash attack from Final Fantasy VII Remake, and a perfect dodge inspired by Breath of the Wild. Weapon data is a scriptable object template. It stores the unchanging variables like weapon type, prefab, animator override controller, and attack data. Attack data and hit data store things like damage, hit stop, camera shake, and knockback. Then the run-type weapon class uses that template, but also tracks states that change during gameplay, like the current attack index, current multi-hit index, register colliders, and more. Originally, I had this mixed together, but that became a problem. Runtime states like combo index or active colliders should not mutate the original scriptable object asset. Once I separated the template data from the runtime data, the system became much more scalable. With that in mind, we can talk about the attacks. Attack windows are animation timed, but the timing comes from attack data. When the player is in an attack animation, an attack hitbox SMB reads normalized animation time, which allows us to see if we are in an active hit window. During it, it enables weapon colliders and turns them off otherwise. When a weapon collider hits something that implements iHittable, it calls got hit function. From there, the hit response handles damage, hit stop, VFX, camera shake, plus knockback if the target supports it. I separated hit response from knockback response. iHittable handles receiving hits, while iKnockable is checked separately for objects that should also be pushed, launched, or put into a recovery state. That gives me room in the future to have objects that can be hit but don't take knockback, like destructibles or enemies with special reactions. I also preferred handling attack timing with state machine behaviors instead of putting animation events directly into imported FBX clips. It made the timing easier to reuse, inspect, and keep connected to the attack data. Going deeper into combat feel, hit stop was one of the most important additions. In a previous project, I treated hit stop more like a state, but for this project, I treated it as a universal locomotion layer. The reason is that hit stop should work no matter what state the character is in. I don't want hit stop to destroy the current state, I want it to pause the current context and resume it afterward. So both player and enemy locomotion check for hit stop before updating their current state. When hit stop starts, I cache motion values, pause the animator, and stop movement. When it ends, I restore those values and let the current state continue. This made hits feel much more impactful. The downside is that the player and enemy had almost duplicate code with some syntax differences because one uses rigid body and the other uses character controller. If I rebuilt it, I extract that shared hit stop logic into a reusable helper or struct so that different movement drivers can implement this without having duplicate-like code. I also made a perfect dodge system inspired by Breath of the Wild. From the player's perspective, if they dodge an attack at the right time slows down and they get a chance to counterattack. Technically, when the player enters dodge, the system checks nearby weapon holders to see if any enemy weapon is currently in a perfect dodgeable window. This is important because perfect dodge is tied to weapon timing, not just enemy state names. Enemy weapons expose a perfect dodgeable window near the active hitbox timing, and the runtime weapon tracks whether it can currently be perfect dodged. Initially, I thought about calculating incoming attack trajectories and checking if the dodge would avoid the attack within a small window, but that was more complicated than it needed to be. It also became less forgiving. So instead of asking, is the player mathematically dodging this exact incoming attack, the system asked, was the player in reasonable danger when they initiated the dodge? That made the mechanic easier to implement and gave it the right level of forgiveness for this kind of combat. The dash attack was inspired by Final Fantasy VII Remake, mainly Cloud's ability to close distance toward the target when attacking. If the player starts the first attack in the combo chain, the system searches for hittable targets within range. It picks the best target based on player directional input. If there is no directional input, it uses the character's model's forward direction. This helped make combat feel faster and more alive. A future improvement would be obstacle checks because right now target acquisition is mostly angle and range based. For responsiveness, I added an attack buffer. If the player presses attack slightly before the combo follow-up window opens, the input is stored and triggered when the attack becomes valid. The animation event script checks how recently attack was pressed, and if it is within the player's buffer window, it triggers the next attack immediately when the follow-up window opens. This makes the combo system feel more forgiving without letting the player cancel attacks at any time. Another system that supports combat is the lock-on camera. The player-facing result is simple. When the player locks onto an enemy, the camera frames both the player and the target, and the player movement and model rotation work around that target. But the camera itself was more involved because I didn't want it to be a static camera or rely entirely on a basic target group. The lock-on camera calculates the midpoint between the player and target, uses yaw and pitch to orbit around them, and solves the camera distance based on a field of view, aspect ratio, horizontal spacing, and vertical spacing. That way both characters stay inside the frame. I also added smoothing for midpoint distance and rotation, so knockback and movement would not make the camera snap too harshly. For the bow, holding aim switches to an over-the-shoulder camera and shows a crosshair. For its animation, I used an avatar mask and animation layer, so only the top half of the model is affected by the bow animations. That way, the movement animation can still play while aiming. When aiming, I spherecast from the crosshair to find the aim point. I stored that position in an invisible aim target object, which gives the arrow a clean target to shoot toward when the player releases. I use spherecast instead of perfect raycast to make aiming more forgiving. The arrow itself also uses spherecasting during flight instead of relying only on gliders for better hit detection. Since the arrow moves quickly, this helps prevent it from skipping past objects between frames. In a future version, I would pull arrows like I did with the Hit Impact VFX. One practical shortcut I used was that instead of building a more complex upper body rig aiming system, I rotated the whole character toward the aim direction and used the camera angle to hide it. From the player's perspective, it worked nicely and it avoided unnecessary complexity. I even had a few people look at the aiming system to see if they noticed, and they didn't. Moving away from combat, another major system I made was Dialogue. The Dialogue Manager took longer than expected because it ended up behaving almost like a mini timeline. Play Conversation uses coroutines and do-tween to fade in the UI, change talker animations if needed, position the camera, fade or type out text, wait for input or timers, and then handle how the conversation ends. The conversation can end in three main ways. Default just fades out the UI and ends the dialogue state. Custom executes a custom action, like giving the player an item or skill point. Choice displays a choice UI where each choice can start a new conversation, ends the current one, or executes a custom action. The custom end action pattern uses scriptable objects. Each custom action inherits from conversation end action and implements execute. That kept the reward logic out of the dialogue manager and made the system easier to extend. The conversation data itself is stored in conversation scriptable objects. Sentences can define text, entrance style, camera behavior, optional animation changes, timing, choices, and custom end actions. Once the core play conversation flow was done, creating content became much easier. Different conversation, make a new conversation asset. Need a reward, use a custom conversation end action. Need a different camera angle, set the sentence camera settings in the editor. This also connected dialogue to progression. NPC conversations give items, give skill points, update talker state, or unlock parts of the player's kit. So dialogue was not just text, it became part of the gameplay loop. This is one of the systems I was happiest with because it became very developer friendly. Staying in the UI side of things, we have the pause menu. The pause menu is a canvas with multiple panels spaced out, which I call tabs. The pause menu manager handles the shared navigation, page transitions, sliding, fading, and which menu tab is currently active. Each tab has its own manager that extends pause menu tab base. So the main pause manager owns the overall navigation and presentation, while each tab owns its own behavior. The map tab is pretty simple. It is a lightweight progress screen that uses a top-down camera render to a texture, and I only render it when the map tab becomes active. The skill tree unlocks abilities like dash tag and perfect dodge, plus attack and defense upgrades. Unlocking one skill only unlocks the next skill in that row, which I manage through button navigation and unlock states. For the inventory menu, I want to explain both the menu and the actual inventory equipment systems, because they are tightly connected. On initialization, the inventory menu manager builds buttons from the player's own weapons and customization items. Selecting an item shows descriptions, icons, and equipment behavior. Items are scriptable object assets. Inventory item data defines shared item fields like item ID, display name, description, icon, and item type. Weapon item data wraps a weapon data asset plus equip rules. Customization item data has a customization slot and a visual prefab, and key item data is currently a marker type with no extra fields. Ownership of items is handled by player inventory. It keeps a serialized list of owned item assets for iteration and a runtime hash set of item IDs for fast ownership checks and duplicate prevention. The inventory itself does not apply items to the player, it only answers questions like, does the player own this item, and give me owned item of this type. So the inventory menu is basically a browser for the inventory. The equipment logic lives in player equipment. When the player clicks on an item, Smart Equip decides what to do based on the item type. It also handles equip and unequip behavior while respecting equipment rules. For example, an offhand weapon requires a valid main hand weapon. The most important equipment function is refresh weapon equipment. When weapon equipment changes, it clears previous weapon stats and visuals, spawns the new weapon prefab into the player's hands, updates the active weapon data, registers weapon colliders, updates combat stats, and swaps the animator override controller so the player uses the correct attack animations. This is where the system's really connected. The inventory menu drives equipment updates the player visuals and stats, and those changes feed back into the combat through the active weapon data. Customization uses a similar idea, but instead of changing combat data, it changes visual prefabs on the player and preview model. I don't want to overstate the save system as the start of the project, but it was important because it would force the systems to work together. Inventory, equipment, NPC, progress, chests, enemy settings, and player state all needed to restore cleanly. The Save Game Manager on Save builds a game save data object that stores things like player data, inventory IDs, equipped items, skill unlocks, settings, enemies, chests, and talker state. Then the save system writes it as JSON to application.persistent data path. On load, the game fades to black, disables input, and restores the game state based on the save file. For the scope of a single player prototype, readable JSON was enough. For a larger game, I would add save versioning, multiple save files, and a sturdier format with better protection. The last major feature I want to talk about is enemies. From the player's perspective, enemies patrol, detect the player, chase, attack, retreat if they go too far from base, strafe around the player, or keep distance to shoot arrows. I split enemies into 3 layers: Brain, Locomotion, and Combat. Locomotion handles movement, Brain decides what the enemy wants to do, and Combat subclasses define how the enemy fights. There's also an enemy script that acts as the bridge between these layers. Enemy movement uses a mix of nav mesh and character controller. The nav mesh calculates path direction, but Locomotion drives the actual movement. I did this because nav mesh is great for pathfinding, but it is also not built for things like knockback. I wanted all enemy movement states to stay consistent whether the enemy was patrolling, chasing, recovering, or being knocked back. The Brain decides the enemy's high level intention. It has states like idle, decide, patrol, return to base, and combat. When the Brain enters combat, it starts the enemy combat epicenter. When the Brain leaves combat, it stops the combat cycle. The combat architecture is where I feel the enemy system is strongest. Each enemy combat type inherits from enemy combat base. The base handles common behavior like getting hit, idle behavior, alerted behavior, and target setup. Then each child class adds what makes that enemy different. Melee enemies add chase and attack behavior. Strafer enemies build on melee enemies by adding a strafe state before engaging. Long range enemies add keep distance behavior before shooting projectiles. So the base combat class handles the shared foundation, while the subclasses define the combat flow for each enemy type. That made it easier to add different enemy behaviors without rewriting the same combat logic every time. A project of this size was a first for me, so I learned a lot. The first big lesson is that the Finite State Machine Foundation was worth it. It kept complex behavior readable and scalable, and it is a pattern I'll carry into the future projects. The second lesson is that I should build item systems before weapon systems if weapons are items. I built weapons first because I needed combat early, but since weapons eventually became inventory items, I had to adapt the item system around decisions I had already made. Fortunately, because I had already separated weapon and weapon data, the implementation went smoother than expected, but the order of decisions could have easily caused problems if the weapon system had been structured differently. So from now on, whenever I implement a system, I'm going to consider timing and its cohesion with not just the current systems, but future systems as well. The third lesson is to separate game state management from settings and global references. The game manager became responsible for a lot: play mode, pause, VFX, combat music layers, UI references, and more. In a larger project, I would split that into cleaner managers or service style references. The fourth lesson is that scope shortcuts are sometimes the right answer. Originally, I wanted a magic system, but I cut it because I wanted the existing combat systems to feel more polished. Magic would have required more VFX work, and my strongest focus was gameplay programming, not tech art. For this project, considering the time I gave myself to do this, it was better to have slightly less content at a higher polish level than more content with less polish. The bow aiming is another example. I could have built a more complex rigging solution, but rotating the whole player and using the camera angle gave me the result I needed without adding unnecessary complexity. This project started as a mix between passion project and a portfolio piece, with the portfolio side taking priority, but I really loved how it turned out, so in the future I may return to it and expand it into a fuller game. I covered the main mechanics and systems, but there is still content I did not go too deep into because I wanted to keep this devlog focused, so make sure to play the demo and check everything out. If you want to get a better perception of the code structure, you can check out the project repository. Also, make sure to look at the credits document, which lists the people involved in the creation of the art and audio assets used in the prototype. With that being said, I hope you enjoyed the Tiniest Adventure devlog. If you have any questions, feedback, want to report bugs, have suggestions, would like to learn more about the demo, or just want to connect, please reach out to me. Thanks for watching.